Good morning, everyone. Welcome to the class. Today, I'm going to give a lecture on chip Pdn designs. So far in this class, I was talking about the basic principles of power distribution network. We was talking about impedance requirement and inductance and decoupling capacitance. And we was talking about resonances. Also, I said that we have hierarchical design approaches. On-chip decoupling capacitors are responsible for high frequency fast switching current. Meanwhile, PCB and package level decoupling capacitors have functions to supply the switching current at megahertz to 100 megahertz ranges. So to make a low impedance solution for Pdn designs, we need to put hierarchical decoupling capacitor designs. And one approach is to have decoupling capacitor at PCB and package levels. And today, I'm going to give a lecture on-chip Pdn designs. As I mentioned before, on-chip Pdn is responsible for over gigahertz range switching current. So if you want to reduce the EMI and PSIJ at gigahertz range, this will be very important for 5G networks and high-speed data rate interconnection. So this subject, on-chip Pdn designs, are becoming more and more important. Once again, I would like to review overall feature of Pdn impedance. As we have discussed previously, in the kilohertz range, PCB and package level VRM decoupling capacitor are very responsible and effective to bring the impedance down to low impedance. And at the megahertz range, we usually have PCB package decoupling capacitance, but because of parallel resonances and serial resonances, we have high impedance peaks and low impedance peaks. And minimal value of impedance in these ranges are determined by equivalent serial resistance. Now, from 10 megahertz, impedance will increase at higher and higher frequencies. That is because of PCB and package level Pdn inductances. And this inductance is generated by tracing or plane structures of at package and PCB levels. As you know, any interconnections which has less than 100 micrometers still has contribution to the inductance. In the meantime, we're gonna have a plane resonance that will be covered at Monday class of next week. And if we have planar structures at PCB and package, it's gonna generate the resonances. We gotta be very careful about these resonances, especially for EMI reductions. And these resonances are generated by decoupling capacitor resonances. In the gigahertz range, we wanna bring it down the impedance. Very effective and only way to do that is to put on-chip decoupling capacitors. The reason it has very low self-inductance and interconnection inductance. So we can bring it down the impedance by putting the capacitors. But this on-chip capacitor is very expensive solution. But the only way we can bring the impedance down to low impedance is on-chip decoupling capacitor. That is the subject of class today. But on-chip in PDN interconnection also has some resistance. Decoupling capacitor itself has some resistance. So because of that, the impedance limit will be shown up at this frequency range, and eventually impedance will go up again because of on-chip inductance of PDN network. So anyway, in this class today, I'm going to talk about how to generate the on-chip decoupling capacitors and how to minimize on-chip resistance and how to minimize on-chip inductance. That is going to be the subject of class today. As I told you just previously, we have three different elements at gigahertz range: on-chip capacitance and on-chip resistance and on-chip inductances. Also, I wanted to emphasize that we're gonna generate another resonance by having on-chip decoupling capacitors. Usually this resonance occurs between a frequency range between 100 megahertz to gigahertz. That is generated by parallel resonance between package PCB level inductance and on-chip capacitance. Now let's start to talk about on-chip capacitance. There are many different types of on-chip decoupling capacitors. First, I would like to give you an example of interconnection capacitance, especially between power and ground. We may have three different type capacitance. First one is line-to-line capacitance. One line is power line, the other one is ground line. Any metal lines which are facing each other will create capacitance. Also inside the chip, we can have some grid type capacitance or some partially plane-to-plane capacitance. So inside chip, if you have power metal and if you have ground metal, between them, you're gonna have capacitance. This capacitance will partly serve as decoupling capacitance. You may remember that to increase the capacitance, to bring it down this impedance at one frequency, one range, you have to maximize the capacitance. So that means when you are designing power and ground metals inside chip, you have to design the metal structure which has maximum capacitance between power and ground plane. You remember that in order to increase the capacitance, you remember that capacitance is epsilon multiplied by surface divided by thickness. This is plane type capacitance. So in order to increase the decoupling capacitance, which is generated by line to line or plane to plane or grid to grid, you have to minimize the distance between the power metal to ground metal. And also you have to maximize the surface area which interface between power and ground metal. So planar type with the maximum area will be very helpful. In addition to that, you have to fill this dielectric material who has the highest dielectric constant. high K material will help to maximize the capacitance. On the left side, there is an example. Let's assume that inside your chip, let's assume that this is the silicon chip, and there is a metal wires, finger type metal wires that is connected to power to the external package or PCB. By having finger type power distribution network, we can minimize the area covered by power and ground metal, or you can minimize the number of metal layers inside the chip. Also, you may have some finger type metal lines inside chip to make a connection of ground of off-chip. Off-chip means the package level and PCB level ground. Eventually, this ground will be connected to shash or external ground. In this finger type configuration, metal and metal will face each other, and power metal and ground metal will face each other. So we're gonna have some distributed type capacitance. This is a little bit unintentional parasitic capacitance, but that will constitute as a decoupling capacitor. So once again, if you want to maximize the decoupling capacitors, you have to reduce distance between the fingers, and also you have to fill dielectric material who has highest number. So if decreasing the distance between the power and ground finger means that number of fingers should be increased. And that means the more and more your chip area will be covered by this power and ground metal. But later I'm gonna come back to this issue again. But eventually, as I told you that in region 2, it is determined by resistance, and region 3, it will be determined by inductance. Probably above maybe 100 gigahertz or like that, inductance will be dominant. And from 10 to 30 gigahertz, probably this capacitance will be dominant PDN contribution. But here in this case, because we are using long interconnection line, so R is gonna increase. And also because of long interconnection, we're gonna have large inductance. So finger type may not be very suitable for very, very high frequency or high performance silicon chip. Probably this might be useful for moderate performance, moderate speed digital chip PDN designs. But at this moment, what I'm saying at this moment is that any type of power and ground PDN design inside chip is gonna generate the parasitic decoupling capacitance between power metal to ground metal. Another type of decoupling capacitor is, I would say, grid type decoupling capacitors. Rather than having finger, we have grid type power lines, and also ground has the grid type. The advantage of grid type capacitance is that we can reduce resistance and we can reduce inductance, because the loop inductance generated by this grid is actually will be determined by area of this small square, which is formed by power and ground grid. Meanwhile, in the grid type, we have some large area between the power and ground. That's why we have higher inductance. So this mesh type, or sometimes we can call it as a grid type, or sometimes we can say it is a mesh type. We're gonna have smaller, so this might be more suitable for high performance silicon chip, digital chip power and ground design, Pdn design. Here also I want to say that inside grid, the metal will see each other, they will face each other, and it's gonna work as a decoupling capacitor. Of course, if you want to reduce the decoupling capacitance, you have to reduce the distance between power and ground metal, and you have to choose dielectric material which has higher dielectric constant. Smaller d means the smaller grid size, and then means the number of grid has to increase, and it will use more and more surface area of silicon chip for power and ground. The best case is to put power and ground metal cover the whole surface area, but there are certain design rules because of fabrication and limitations. There are certain percent of power and metal that could be covering on the chip, on the surface of the chip. So somehow I think inside the chip, this power grid type PDN might be very suitable for low impedance PDN designs. But the size of this grid, the size of this length of this grid will become smaller and smaller as the switching frequency and current is becoming higher and higher. Now, in this class, I am talking about the line-to-line and capacitance which occurs between power and ground metals inside chip. Yes, second type of decoupling capacitor is a plain metal to metal capacitance. So probably sometimes it is possible, sometimes it is not possible, but let's assume that you have a big silicon chip. Some part of your silicon chip may be covered by power plane and ground plane. This is an example. This may not be usual case, but this is cross-sectional view of a metal structure inside your chip. And I'm assuming that it has power plane metal. Metal 2 is wholly dedicated for power metal in this configuration. Metal 5 is wholly dedicated to 5. In the previous slide of finger and grid type, same metal plane can be used for local signal interconnections. Sometimes active transistor or gate metal can be placed in this metal plane, but in this configuration, metal 2 is wholly dedicated for power, and metal 5 is wholly dedicated for power, and probably metal 5 could be used for I/O power, metal 5 power could be used for core power, and metal 8 power could be used for PLL. There might be many different type of assignment. If you believe that you have to choose which metal is going to be used, because depending on which metal you use, you're gonna have different resistance and different inductance. So you have to choose the right metal plane for each cases. And we are assuming that metal 8 is used for PLL power. For each cases, we have to put ground metal as close as possible, and you have to put ground at adjacent layers. We have to put ground. So let's assume that you have 20 metal layers for your high performance silicon chips. Probably more than 10 metal layers may be used for power and ground in the near future. Probably because of that, the number of metal layers in the silicon chip will increase more and more. And another trend is that we're gonna use more TSV and more TSV. All this design complexity and cost are coming from the signal integrity requirement. So when we have this power and ground metal planes inside a chip, you're gonna create the capacitance, and that will work as a decoupling capacitor. Unintentional or intentional decoupling capacitors. And you gotta choose dielectric material who has higher number. Also, you have to reduce the thickness of this insulator between power and ground as thin as possible. That is another decoupling capacitor contribution of this decoupling capacitor is generated by parasitic capacitance between power metal and ground metals inside chip. Number 3, which has very important role in decoupling capacitor design inside chip, is gate oxide capacitance. Why the gate oxide capacitance is so important? I would say the dielectric thickness which form the gate oxide is the thinnest dielectric material inside the chip. In the previous slide, I would say the distance thickness between power ground plane could be around 1000 angstrom for conventional metal insulator metal fabrication and stack up inside the silicon. Here, the D might be around millimeter range. Here, it might be millimeter range. Here also, finger size might be millimeter range, or some case 100 micrometer range, millimeter range. So this, I'm sorry, the length of length is the millimeter range. The length is millimeter range. I'm sorry. Here the grid length size is the 100 micrometer range. And that is important to form the capacitance, parasitic capacitance. Here it has 1000 angstrom range in the between the metals on the top of the silicon chip. But this gate oxide dielectric could be in a range of 10 angstrom to 50 angstrom. So with the given area, D is 100 angstrom range. So there's this capacitance is very area efficient. Let's assume that this is your silicon chip size 1 centimeter by 1 centimeter. This is most expensive area in the world, probably as expensive as your diamond. So we need some decoupling capacitors. We need some decoupling capacitors, but we want to minimize the area to reduce the cost. So in that regard, gate capacitance is most useful capacitance inside chip. For example, let's assume that you have dielectric material who has dielectric constant 10. I think silicon dioxide dielectric constant is near 10. And we are assuming that this chip has the decoupling capacitor size of 1 millimeter by 1 millimeter. And roughly, I estimated the capacitance by 1 millimeter by 1 millimeter size. And we found the 100 nanofarad can be formed inside the chip. But please remember that at the PCB and package level, we can put 100 nanofarad. So capacitor size of on-chip decoupling capacitor is not that huge. This off-chip decoupling capacitor C is much higher than on-chip, but it has smaller resistance and smaller inductance. So this is very useful area for gate oxide capacitance, especially in gigahertz range. Compared to off-chip capacitance, C is not that big. Even though we have 1 meter by 1 millimeter size, the capacitance is 100 nanofarad. So it is not big, but it is very suitable for high frequency decoupling capacitors. But in our life, nothing is free. There's no free lunch. If we take some advantage of something, some disadvantage will come along with that. They are accompanying each other. The disadvantage of this on-chip decoupling capacitor is that probably some potential leakage probability, some leakage issue, or sometimes if you are breaking this dielectric, electron will leakage. So it's potentially it's gonna have leakage problem if your dielectric of very thin material is not a perfect material. You're gonna have some risk of leakage. Second thing is higher ESR. Please look at that. If you want to make a capacitance, one metal, usually that could be tungsten or some material inside your chip, and it's gonna be connected to power or gate, whatever. And opposite metal is channel. This is silicon channel of CMOS structure, metal oxide silicon structure. And at the end, you have to connect source and drain. This channel is not perfect metal, it is silicon channel. So depending on the bias and doping and temperature, you're gonna have different mobility, and so you're gonna have some channel resistance. So because of that, you have resistance, nonlinear resistance. For example, depending on your bias, this is CMOS structure, you're gonna have different oxide CMOS capacitance. That's okay. Your capacitance is now becoming a nonlinear device, and it's gonna bias dependent. You remember that in the CMOS, I think, class, depending on bias, capacitance changes. depending on depletion, accumulations, and some CMOS theory is telling that this resistance has bias dependent. And in addition to that, more important thing is that it has channel resistance. It is depending on bias, temperature, doping, and mobilities, and there are so many factors. Because of that, you have higher ESR. So I think this gate oxide capacitance is very usable in this range of 1. Somewhere in the frequency range, you need large capacitance. This is very effective way with a given area of on-chip, but the limitation is coming from the self-resistance of this gate oxide capacitance. Depending on grid size, you may have some area. If you use the large size capacitance, gate capacitance, this channel resistance will increase. So one approach is that you make a very small size capacitance and you make a power grid and ground grid. And this grid size is making as small as possible. Then this channel length will be decreased, and we can minimize the ESR. In summary, I would tell you that we need on-chip decoupling capacitance for high frequency ranges, and there are some parasitic capacitances between power and ground on-chip metals. Now, number 3 example is intentional on-chip decoupling capacitors, and most area efficient capacitance solution is gate oxide capacitance. But now gate oxide capacitance has channel resistance. So in order to minimize the effect of channel resistance, we have to make a very small size gate capacitance and increase the number of gate capacitance. A small size, many. And one way to do that is you design grid type of power and ground on-chip design. And in each grid, you add decoupling capacitor with gate oxide. But now, I would like to move on a little bit further. So far, I was talking about this gate capacitance that is quite intentional. But let's assume that you are connecting power to this source. Then we're gonna have parasitic capacitance between source and gate, and parasitic capacitance between source and drain. Sometimes we have parasitic capacitance between drain to substrate. And substrate also has some capacitance. So we're gonna have additional parasitic capacitances. Some of them are intended or some of them are unintended. So when you are designing on-chip PDNs and you want to estimate how much impedance you may have inside on-chip PDN, you have to include all these parasitics. And you have to fight against ESL and ESR. Number 1 approach is that you have to maximize the decoupling capacitors, and you have to include the parasitic element of all the capacitances, which you may not consider in your circuit design. Eventually, you have to fight against essential ESR and essential ESL. Anytime you have metal structures to make a capacitance, you have ESR and ESL. Chun-sang, are you there? Can you speak?
네, 교수님.
요 페이지 한번 요약해 보시겠습니까?
네, 온집 캐패시터로, 그, 트랜지스터의 게이트 옥사이드 캐패시턴스가 이제 면적들이 굉장히 효율적으로 적용을 할 수 있는데, 그래서 이제 온집에서 이 트랜지스터에 의한 게이트로 이제 결국엔 ESR과 ESL을 해결을 해야 된다고 이렇게 말씀을 하셨고, 그 와중에 이제 정확한 값을 다 적용하기 위해서는 파라시스 값들을 모두 적용해서 그걸 따져봐야 된다고 말씀을 하셨습니다.
그렇습니다. 그렇습니다. 하여튼 C를 맥시마이즈 해야 되는데 생각보다 파라시틱 컴포넌트들이 되게 많더라. 우리가 보통 시그널 디자인, 우리 그 대학교 다닐 때 게이트 트랜지스터 모델 이런 거 했을 텐데 이런 캐패시턴스들 하여튼 인사이드 칩에 파워 그랜드는 캐패시턴스가 다 도움이 되더라. 그 얘기고 캐패시턴스 다 열심히 만들고 나서는 ESR과 ESL을 줄이는 거를 상당히 심도 있게 봐야 된다 이 얘기했습니다. 종현이 이야기할 수 있나요? 지금 마이크 연결이 되나요?
네, 그렇습니다.
한번 요 페이지에 게이트 옥사이드 캐패시턴스가 어떤 장점이 있고 어떤 단점이 있는지 한번 얘기해 보시겠습니까?
싱거 타입의 같은 경우에는 싱거 타입이나 다른 타입의 경우에는 이 옥사이드 캐패시터의 두께 부분에 좀 단점이 있었는데 게이트 옥사이드 캐패시턴스를 사용을 함으로써 이 두께를 작게 가져와서 좀 더 큰 캐패시턴스를 얻을 수 있는 장점이 있습니다. 하지만 이제 이걸 사용하다 보면은 좀 디케이지가 발생할 수 있고 ESR이 높아진다는 단점이 있다고 이해를 했습니다.
네, 그렇습니다. 에어리어 입장에서 게이트 캡이 되게 좋은데 저항이 커요. 그래서 작게 쪼개는 방법을 씁니다. 그 채널 저항을 줄이려고 이 방법도 온칩 PDN에서 D캡의 크기의 한 반은 이걸로 차지하는 것 같습니다. Now, I would like to talk about another type of decoupling capacitor that is intended or unintended. You remember that a three-dimensional structure is very useful for high-speed interconnections to maximize the data bandwidth between GPU and memory. Also, the advantage of TSV is that TSV has this thickness of our substrate in the future gonna be less than 30 micrometer. The length of this interconnection is very short, so TSV gonna have very low inductance. You remember that in the PDN impedance is gonna go up and go down again. This inductance also we have to reduce. This inductance contribution is coming from PCB and package level. By using TSV and number of TSVs increase, then we're gonna reduce the power ground PDN impedance. That is why I'm constantly keep saying that TSV is very essential interconnection structure for next generation chip and packages. But when you are designing the chip with the TSV, whenever you have a power TSV, this is top view, you have to have ground TSV has to be placed as close as possible. Always power TSV and ground TSV has to be designed in a coupled fashion. They has to be paired. Why do we do that? By reducing the distance between power and ground TSV, we can reduce the inductance of TSV. By increasing the number of TSV, also we can reduce the inductance of TSV. Another contribution of TSV is that we're gonna generate this capacitance between power TSV and ground TSV. Even though this is not big number, but still I believe that this TSV will be of some contributors for on-chip decoupling capacitor design. So if you are designing this PDN impedance at the chip level or this level, I would suggest to include the TSV effect. One of the contribution of TSV is the inductance will be reduced in this frequency range, and you can increase the capacitance in this frequency range. This inductance is actually mainly from on-chip interconnection, and TSV is responsible or helpful in a range of this frequency range. Now, I would like to talk about the decoupling capacitors, characteristics, capacitance component formed by TSV. When we have power TSV, we have metal structure, and if we have ground TSV, it has metal structure. So as far as you have metal and metal, they are looking at each other, we can generate the silicon, the decoupling capacitors. If we look at more carefully inside, we have some capacitance formed by silicon oxide film surrounding the TSV metal that is here. Silicon oxide. Also, silicon itself has some capacitance. So in the case of TSV to TSV capacitance, we have three different types of capacitance. Number one is TSV oxide capacitance, and TSV silicon substrate capacitance and resistance. Of course, silicon substrate has certain resistance. It is gonna contribute to the ESR. In this slide, I'm trying to explain the contribution of TSV capacitance for decoupling capacitors. Now, another type of, I would like to give you another type of capacitance that is called MIM capacitance for decoupling capacitor. That is very intentionally designed metal to metal capacitance inside the chip, and we want to put very high K material. It could be more than 10, or could be more than 100, or could be more than 10 to 3 or 10 to 6. I'm expecting very, very high dielectric material sandwich between the power and ground metal. I'm assuming the thickness of this metal could be less than 1000 angstrom. The advantage of this MIM capacitance is that resistance is very small compared to TSV. TSV has silicon resistance, and the gate oxide film has this gate resistance. But this metal has very little bit of resistance because of this metal plane, and it has a little bit of resistance in the ground plane inside chip. If you have whole chip, some part of that area may have this kind of MIM capacitance. The advantage of MIM capacitance is that still underneath of this MIM capacitance, we can have gate oxide active, because vertically this MIM structure can be placed on the top of oxide gate capacitance, because layer is different and processing is different. The advantage of this is resistance is very small, so we can reduce very low resistance compared to gate oxide capacitance. So I think this is very useful decoupling capacitor over 30 gigahertz. very, very high frequency, if you want to put on-chip decoupling capacitors, I would like to push you very hard to add MIM type on-chip decoupling capacitors. We need some help from the processing and materials scientist who has to develop some very high K material. In the future could be K could be more than 1,000 or million number. And still in those cases, we want to keep the thickness as thin as possible. And then we can increase the capacitance and reduce the resistance. And eventually this inductance is will be determined the grid size. If you are using very small grid size, you're gonna have a lower and lower ESR. This MIM capacitance is very, very important and useful and strong, powerful solution for on-chip decoupling capacitors. Now, so far I was talking about the capacitances of on-chip PDN. I started with the parasitic capacitance between line to line. I was talking about the metal plane capacitance, and I was talking about gate oxide capacitance and parasitic capacitance and TS3 capacitance and MIM capacitance. All these capacitance will combine together to make a on-chip PDN decoupling capacitance. So when you are designing on-chip PDN, you should be carefully include all these elements, and you have to properly decide the design parameters. Also, among these 6 different capacitances, some of them are very effective at higher frequencies because it has smaller resistance and smaller inductance. And some of this capacitance is more effective in the some frequency ranges because it has larger capacitance, but it has larger resistance as well. So hierarchically, inside chip still, you have to design in hierarchical way. I told you that eventually inductance will determine the impedance at a very high frequency range. So I would like to talk a little bit about the inductance. Let's assume that you have ground metal plane, and let's assume that you have metal on the top, and I'm assuming that the length is L and thickness between the power and ground metal is D, and we assume that width of this metal is W. Then roughly I would say inductance is mostly importantly proportional to length of this interconnection. So that's why I keep saying that at a higher and higher frequency, we have to reduce the length of interconnection between decoupling capacitors and I/O switching devices. Also, decoupling size should be very small because decoupling capacitor itself is gonna have self-inductance that will contribute this inductance as well. And second contribution is magnetic permeability, and I'm sure that we are usually 99% we are not going to use the magnetic material on the chip unless you are making some sensors which feels magnetic field, such as current sensors or MEMS sensor. In some applications, you may have some magnetic permeability, magnetic material, but one interesting thing is that in the gigahertz range, I couldn't see any magnetic materials. They are becoming normal material at the gigahertz range. So magnetic permeability is going to be almost the same. Number one parameter is the reducing the length of interconnection. Second physical parameters that is really controlling the inductance is the width of your metal. So in signal line, you design W and D to make a 50 ohm. But in power and ground case, to minimize the inductance, you have to maximize the width. So you have to make a wider and wider materials. In signal line, this kind of interconnection structure is typical, but in power and ground, you have to have metal and ground plane as wider as possible to minimize the inductance and to maximize the capacitance. Last thing is to reduce the thickness. Thinner metal will help. So design rule is that make power and ground metal as close as possible and as wide as possible and make very short interconnection. So we have to make D as thin as possible. W should be made as wide as possible. That is the design rule of power and ground metal, especially when we look at the inductance. That is going to control this area. But decoupling capacitor itself has always some dimensions, and interconnection has always dimensions. Sometime in the long future, this dimension could become to nanometer or atomic scale. But as far as I know, in current technology, L could be minimally 100 micrometer range, because there are certain transistor area and decoupling capacitor area inside chip. L is gonna be always 100 micrometer range. And the last design parameters that will reduce the inductance is the number of interconnection. If you have more interconnection, the effective inductance will be reduced by divided by number n. So number one approach to reduce the inductance is to reduce the length of interconnections. Second approach is to increase the number of interconnection. That's why I'm keep saying that TS4 is the solution. Now, so far we was talking about on-chip PDN. I was talking about on-chip PDN. That means now I'm a little bit want to talk about on-package PDN together. If you have transistor inside the chip, if you have a finger type PDN inside chip, you may have decoupling capacitor adjacent. So loop inductance is controlled by the loop size of this small loop. I said this is loop 1. This loop size will be determined by the grid size and the distance from your transistor switching circuit and decoupling capacitors. To reduce this loop 1 size, you have to put on-chip decoupling capacitors as close as possible to your switching current, switching transistors. That will control the inductance of loop 1. That is the design rule. In this frequency range, you have to put decoupling capacitors as adjacent as possible to your switching current transistors. Sometimes that could be core transistors, sometimes that could be IO transistors. You have to put this decoupling capacitors as close as possible. That will control the loop inductance of loop 1. But that is the case where your switching current has the frequency components of gigahertz range. Sometimes, depending on your data patterns or depending on your switching operation, your switching current has some frequency spectrum of 100 megahertz. That current is actually supplied from on-package decoupling capacitors, and you have on-chip decoupling capacitor has certain self-ESL, and you have package loop inductance, and you have on-chip loop inductance. So this whole loop that is much bigger than loop 1, that is controlling the loop inductance of off-chip package PDN. Actually, that is controlling this inductance, loop 2. You remember that there is some distance between loop 2 and loop 1 inductance. That is because loop 2 has much larger inductance. That is the difference between this inductance loop and this inductance loop. But even though you have large number of amount of off-chip decoupling capacitance, it is not effective at higher frequency range because higher frequency is controlled by on-chip PDN. So another message here is that depending on frequencies, you're gonna have different current loop and you're gonna have different inductance. And off-chip decoupling capacitor has large capacitance. That's why we can reduce the capacitance, but because of inductance, we're gonna have increasing inductance. But in the case of on-chip, you have certain on-chip capacitance, but eventually inductance will increase. So depending on frequency range, you're gonna have different loop inductance. And this is now in this slide, I would like to combine two different levels of PDN, on-chip PDN and on-package PDN, and they are having different rules. But anyway, to reduce the on-chip inductance, this on-chip inductance, you have to minimize the loop 1 inductance. How to do that? You have to put this on-chip decoupling capacitors as close as possible. And if you want to reduce the off-chip on-package inductance, you have to reduce the ESL of off-chip decoupling capacitors, and you have to put as close as possible to the chip, and you have to increase the interconnection number as much as possible. That is how we can reduce the inductance. This is for the case of finger type on-chip PDN. This is the case of finger type. This is another drawing. So here I'm assuming that power has a finger. They are connected to package power, and I'm assuming that we have ground finger inside chip, and that is connected to off-chip ground. And we are putting the on-chip decoupling capacitor, and we have switching devices. That was what I was talking about right now. Now, there are another type of PDN, on-chip PDN. This may not be very useful, but some low performance digital chip, if they want to minimize the metal lines and metal layers, they can use this. Here, I'm assuming that we have ring type. Let's assume that we have, this is the silicon, At the edge, we have ground metal, and that is connected to external power. And we have power metal ring, and that are placed as close as possible to power, and that is connected to external power pad. And then this ground is connected to ground of switching device, and this power is connected to power of switching devices. And I'm assuming that we have decoupling capacitors. Then we're gonna have loop. This is on-chip loop, is quite large. And we have external loop from decoupling capacitor to this loop. So depending on your on-chip Pdn designs and placement of decoupling capacitors, you're gonna have different loop for high frequency switching current and low frequency switching current. And depending on your Pdn type, sometimes it could be ring type, or sometimes this could be finger type. This loop 1 and loop 2 inductance will be different. So when you are designing on-chip interconnection, you have to consider the total inductance and resistance when you are choosing different type of Pdn. And sometimes we can use the grid type of Pdn. Then at every grid, we can put the decoupling capacitors. So in this case, loop size will be very small, and off-chip loop size will be relatively small. So grid type might be very good to reduce the resistance and inductance. Now, I would like to conclude my class today to show different type of decoupling capacitors. One of them is hybrid type decoupling capacitors. Let's assume that we have a whole silicon chip, and we have some grid type decoupling capacitor in this area, and we may have some ring type decoupling capacitor on this area. This could be digital processing area GPU might be placed here. Sometimes RF circuit could be placed here. RF chip that use many of switching current, so we can have some relaxed Pdn requirements. Sometimes these metal layers can be used for RF circuit applications such as high Q filter design or high Q inductor designs. So this type, hybrid type on-chip Pdn design could be very useful for SoC design, because SoC has many different capability and functionalities. Some of that area is used for CPU, and some of that area will be used for GPU, and some of that area will be used for NPU. And there might be some analog circuit and RF circuit area they can use this ring type. This is the hybrid type on-chip Pdn designs. Junior, I saw you. Can you tell me a little bit about this slide for me?
네, 교수님. 온칩 PDN 디자인에서 이제 설명해 주셨던 이제 파워그라운드 구조를 이제 하이브리드 형태로 이렇게 싱거 타입, 링 타입, V 타입을 섞어서 사용할 수 있고, 이제 스테몬 칩 같은 구조에서 이제 이러한 하이브리드 형태를 그냥 더 나은 PDN 디자인을 할 수 있다고 말씀하셨습니다.
네, 알겠습니다. 네. 그래서 오늘 이제 깊이 이 얘기를 했고요. 자, 이대로 끝나면 너무 심심할 것 같아서 제가 다른 측정 결과를 좀 보여드리겠습니다. 지금 공유를 하려면 화면 공유. 정현, can you see this slide?
네, 교수님 잘 보입니다.
Yes. Long time ago, I did some works with local semiconductor companies, and I had chance to measure actual simultaneous switching noise and Pdn design effects. I would like to give you some example today. I remember that was 8-bit microcontrollers. There might be many applications to use 8-bit microcontrollers, such as wireless keyboard, refrigerators, and there are some embedded systems that are using this kind of 8-bit microcontrollers. Inside their chip, they had core, digital core, SRAM, and clock circuits, and PLA, and ROM inside chip. And initially, they didn't add any decoupling capacitor inside chip because they didn't know anything about PDN design. So we worked together to add 1.3 nanofarad decoupling capacitors. Some of them are MIM type capacitors, which I was talking about today. Some of them we used oxide capacitance, but mainly we used the MIM type capacitance, and we used this capacitance under the data line, or sometimes we used near the decoupling capacitor near the SRAM sense amplifier. So this blue line is an area we found that we can add some decoupling capacitors inside chip. At the time, clock frequency was really small, very slow, 13.83 megahertz. Right now, we are pursuing 100,000 times faster in these days. And we measure the power supply noise. Without that decoupling capacitors, we measure 840 millivolts. And with this simple 1.3 nanofarad on-chip decoupling capacitors, we was able to measure 270 millivolts. So this was actual power supply noise measures. So without decoupling capacitors, the power switching current switching voltage noise was very high, and with 1.3 nanofarad decoupling capacitor, we was able to bring it down to 270 millivolts. And also, we measured the EMI spectrum from the computing module which used this 8-bit microcontroller. Without that, EMI level was 32.1 dB, and with the decoupling capacitor, it was 21.35 dB. That means the EMI level was reduced by 10 times. More than 10 dB suppression was achieved. And I remember that this chip passed the EMI qualification, and finally they were able to sell this product to their customers. This is very short verification, but I'm very happy to show the function of on-chip decoupling capacitors to suppress the high-frequency noises. At that time, it was 50.5 megahertz range, but now our frequencies of concern is 100 times or 1,000 times higher. So this kind of design, concept, and verification is becoming 100 times or 10,000 times more and more important. I would like to give you another example. We design a package substrate who has embedded capacitors. Please remember that this capacitor is between power and ground metal, and we used a little bit of higher dielectric materials, and we used very thin dielectric material. That is to maximize the capacitance. And also, we put this embedded capacitance up to the very top because we want to reduce the inductance of this via. So this is the case of embedded film capacitance that was included inside the package substrate. Now, by having thin film capacitance, our impedance curve is changed like that. Conventional decoupling capacitors who has 100 nanofarad discrete capacitor of 16, still impedance was very high because of the inductance is higher. Because we are using the embedded capacitance, inductance was reduced significantly in this frequency range. Over gigahertz range, as I told you before, we have to put on-chip decoupling capacitors. This is the embedded capacitors on package substrate. Of course, resonance is frequency shifted to low frequency because the capacitance is increased. But more important thing is that this is actually measurement result. I would like to emphasize that this is measurement result, and we was able to bring it down to inductance from 60 megahertz to gigahertz range. Because of that, so without decoupling capacitor, we had 370 millivolt noise, and with the 16 decoupling capacitors, a discrete capacitor, we was able to bring it down 123 millivolts, and by embedded decoupling capacitors, we was able to bring it down to less than 10 millivolts. The power of inductance. This is power of inductance. How we do that? We use the embedded capacitance effect. Of course, in the gigahertz range, we have to talk about the on-chip impedance designs, but by using the embedded capacitance and by lowering the inductance, we was able to bring the 370 electron millivolt noise to less than 10, about 10 millivolts scale. So once again, I would like to emphasize the significance of the Pdn Designs. 현우 지금 눈이 마주쳐지는데 한번 온칩 Pdn 제 경험을 한번 요약해 봐 주시겠습니까?
교수님께서 그 온칩 PDN을 설계를 하시고 실제 측정할 때 그 디커플링 캐패시터가 있을 때와 없을 때 볼테이지랑 그라운드 플럭추에이션을 확인하셨고, 실제로 그 디커플링 캐패시터가 없을 때는 되게 플럭추에이션이 약 840mV 정도로 되게 크게 나타났는데, 이제 온칩 PDN을 그 디커플링 캐패시터를 배치함으로써 840이었던 게 270mV로 되게 낮아진 것을 통해서 실제 디커플링 캐패시터가 효과가 있다는 것을 실제로 확인을 해주셨습니다.
EMI도 줄었죠, 그죠?
네, 그렇습니다. EMI도
근데
추가적으로 먼저
제가 이게 주장하고 싶은 게 이게 8비트 컴퓨터예요. 진짜 옛날 컴퓨터거든요.
네.
그리고 클락 프리퀀시도 뭐 50메가인가 10메가인가 13메가. 지금은 이게 13기가까지 커지고 전류도 이거에 100배, 클락 프리퀀시, 주파수, 전류 크기가 다 100배씩은 늘었을 것 같아요. 그러니까 이게 얼마나 중요한 디자인 요소인가를 알 수 있을 것 같습니다. 인베디드 캐패시터 얘기도 좀 해주실래요?
네, 그 아까 디커플링 캐패시터에서 설명해 주셨듯이 이제 PDN의 임피던스를 줄이기 위해서는 더 높은 디커플링 캐패시터 값이 사용이 되어져야 하는데, 여기서 보시면 지금 두께가 작아지면 작아질수록, 그리고 다이엘렉트릭 컨스턴트가 높아질수록 이제 디커플링 캐패시터 값이 늘어나게 되고, 이제 그걸 통해서 더 효과적으로
네.
PDN 임피던스를 잡을 수 있다고
그리고 또 하나 중요한 건 여기를 맨 위에 붙여갖고 인덕턴스를 또 줄였어요.
아, 네.
두 가지가 같이 있는 거예요. 그래서 여기 보면 여기를 팍 줄인 거는 캐패시턴스 효과가 크고 인덕턴스 효과가 도미넌트예요. 여기는. 그죠?
네, 그렇습니다.
오늘 수업에서도 계속 강조하고 인덕턴스 강조한 게 이 영역인데 그래서 얼마나 줄였다고요? 노이즈를
300,
디케이 아예
네.
없을 때 120, 370인데 그냥 인베리드. 왜냐면 이 영역이 다 인덕턴스가 컨트롤하는 영역이라 그렇습니다. 네. 더 갈까도 싶은데 그건 다음 주에 또 한번 얘기를 해보겠습니다. 다음 주에는 PCB 레벨로 내려가 보겠습니다. 여러분 오늘 수업 경청해 주셔서 감사드리고 다음 주가 하여튼 이번 주 수요일 날은 또 PSIJ 강의하고 대학원생들이 다음 주까지 계속하면 PDN의 피크를 달릴 것 같은데요. 네, 하여튼 레조넌스 얘기를 또 해볼 텐데 여러분 오늘 수업 집중해 주셔서 감사합니다.